recording on. Oh, now I turned on the recording. So like I said, for the recording, I'll restate it. Chapter 12 material, we're going to start off with some static friction stuff in chapter 8. All right, let's go back to where we were. We're almost at the end of this this chapter, I guess. Chapter 11. All right, so we're discussing the tangential and normal components, and this is an interesting thought experiment. In 2001, a race scheduled at the Texas Motor Speedway was canceled because the normal accelerations were too high and caused some drivers to experience excessive G loads. And these were similar to what a fighter pilot might see. And the concern was that the drivers might actually pass out. So I mean, it's one thing when you're driving during, well, again, I'm not a race car driver, but I'm pretty sure, as with any sport, right? When you're just sort of practicing the loop, as opposed to actually in the moment driving, right? You're going to try to push yourself to the limit. And if they were experiencing excessive G loads during the during just the practice runs, you know that they were going to push it. They're probably going to push it a little too far during the race. So what are some things that could be done to solve this problem? Any ideas? Remember, normal force. What does the normal force depend on? Yeah, I don't even know if there's answers on this slide. Oh, yeah. So reduce the allowed speed, right? Increase the turn radius. So remember, the normal acceleration is a function of the velocity squared, right, divided by the radius. So if you decrease the allowed speed, right, maybe you could do that by putting governors on the cars as well. You would eliminate that risk from one component. Obviously, changing the turn radius is going to be something that's not really easy to do, right? It's something the track's already built. You got to decide, all right, am I going to change the radius? And then have the racers wear G suits, right? This was one other option. Again, kind of pricey, but this is what fighter pilots wear, right? They wear some kind of G suit that it tightens up the rest of your body to keep blood flowing to your head. All right, so we're going to look at this. This is not on, there's two. Yeah, I always get this confused. This is the one, we're just going to go through this one on the slide, and then we'll solve another one very similar to this on the document camera. So here we've got a centrifugal cab, and this would be something that they would actually use to test to put pilots or astronauts through extreme G forces, or you could find it in an amusement park. It tells you the tangential acceleration of the cab is given by this function, right? And they tell you T's in seconds and accelerations meters per second squared. If the centrifuge starts from rest, determine the total acceleration magnitude of the cab after 10 seconds. So this is obviously, this is a fairly simple problem. We're going to just define the coordinate system. You can calculate the tangential and the, or tangential velocity and the acceleration, and then you can calculate the normal acceleration. And then once you have the normal acceleration, right, you can determine the overall acceleration magnitude. So keep in mind, right, this is there's two directions here, normal and tangent. And you always define your normal, right, towards the center of the radius of the circle, or towards the center of the circle. It's along the radius, I guess. And the tangent is, well, tangent to the point of the curve that you're at. Pretty self-explanatory on that. And what all I did here is I put the equations for the acceleration on this page so you can see what they are. And let's see, tangential velocity. So we can start with the tangential velocity first, right? The tangential velocity is just the integral of the tangential acceleration. And we were told initially, right? So, maybe I should put initial conditions in here. It's good to write down your initial conditions, right? At time equals 0, you're starting at time equals 0, which you already know that's your starting point, right? Your initial condition is time equals 0. And you're going to some time t, which happens you integrate it, you get the function of velocity with respect to time. Again, tangential velocity, right? And that gives you 25 meters per second. And then what's your normal acceleration? Normal acceleration is just v squared over rho. Now remember, we wanted to find, really when you do a problem like this, you're going to look at it, you're going to say, okay, I need to know the total acceleration magnitude, right? So you're going to look at these equations, you're going to say, okay, the total acceleration is the sum of the tangent and normal components. I got to figure out what v is to get these components, right? So that's why we figured out v. And remember, we've got, well, dv dt is just this, right? So we have that. We need v squared, so that's what we got. V is 25, r is 8 meters, 25 squared. We get 78.125 meters per second squared. That is the normal component of acceleration. And then you just do a vector triangle, right? So the normal component of acceleration is pointed inward. And then we have a tangential component of acceleration, which has a magnitude of 25. And notice the vector here, right? ET and EN, like you don't know the angles between them, but you could calculate that, because normal is always pointing towards the center of the curve, right? The radius of, or the center point of the radius of curvature. Tangent, in this case, we're given just the magnitudes. Oh, so we do this calculation and we figure out the magnitude of acceleration is 78.285. So the majority is the contribution of the normal acceleration. Let's see. Oh, okay, here's a little group problem. Oh, let me put the poll up there. All right, so the question. Well, background, right? Notice the normal acceleration is much higher than the tangential acceleration, right? So if we go back here somehow. Do we even calculate the tangential? Oh, yeah, well, it's sort of calculated. So 0.25, let's see, tangential, oops. Oh, the normal, oh, what's the tangential? Tangential is 0.5 times 10 squared, yeah, so 25. So normal acceleration is higher than the tangential acceleration. What would happen if, for a given tangential velocity and acceleration, the arm radius was doubled? So instead of an 8 meter, whatever this is, centrifuge, you had a 16 meter centrifuge. So why don't you go ahead and respond to the poll here. Acceleration would remain the same. And you got a whole bunch of different options, right? Normal acceleration would increase, tangential would decrease, they would both increase, or the normal would decrease. I'll give you guys another 30 seconds. Let's see if we can get full participation in this poll. I don't remember if I have the equations on the next slide. All right, well, we got 7 out of 8. I'm gonna sit here. Okay, so let's see, a lot of people answered, majority answered C, A and B. All right, let's think about this in the context of, oops, oh, I don't have the equations. Oh, well, let me go back. So here are the components, right? If we increased the radius to 16, the normal component is going to decrease, right? Remember, our tangential acceleration is given to us, excuse me, as a function of time. So that's independent of the radius, but the normal component is really the one that's dependent on the radius, right? So as that radius increases, you're going to wind up with a decrease in the normal acceleration. So the accelerations would remain the same. Well, yeah, tangential acceleration would remain the same, but the normal acceleration would not, right? We know it's decreasing because rho is increasing. So both of these you can eliminate because of that. And so the correct answer is D, right? AN would decrease. So again, you're going to have this equation. I would write down the general, well, we're going to go through the problems, but the problems we do, I would make sure you understand the equations for them and have them available. All right, let's see. Oh yeah, this is fun. Have you ever seen the weird way an elliptical machine works? How it sort of rotates, or just like this fire hose, right? Fire truck ladders, right? They can rotate about a point. They can rotate around, right? They can go up and down in a theta direction, and then go in and out, right? So we can use these radial and transverse components to analyze systems, and sometimes it's more convenient to choose a system or to choose the analysis method using these radial and transverse components than it is to use X, Y, Z, right? Because a lot of times you'll have just two-dimensional motion that just depends on this theta and R. So this is just another set of equations to confuse you. No, it's just another set of equations that defines the same, the same physical. Oh, let me stop the polling. It defines the same physical conditions just in different coordinates. So here we have a particle P, right? And so you can write this particle if you have a fixed origin, right? You can write it as a distance r from the origin to that point, and then you can also write this this theta vector. Now, if you look at the velocity vector, you're going to get something like this. The velocity vector, because your position vector is a function of ER, and ER depends on both theta and radius, right? It depends on multiple points. Your velocity vector is actually this, both of these are differentiable with respect to time, right? So you've got R with respect to time, ER, plus R theta, E theta. This comes out of just a substitution. Do I have this on the next? I don't know. I might have this in the example. And then your particle acceleration is going to be just the derivative of this, which becomes a little more complicated, right? But you notice all these terms. You've got a theta term. Well, you've got multiple theta terms. First derivative squared, second derivative, You've got r in there, first derivative of r with respect to time, second derivative of r. So lots of terms here to worry about. Just a little bit of note here. This, do not confuse this with what we just covered, right? The acceleration in the r direction is not the same as dvr dt. This is not, so if you're working on a problem in these coordinate systems, you can't just use the rectangular coordinate system acceleration components, right? You have to use this r and theta. So this is the r component, and this is the theta component of acceleration. Oh yeah, this is where the derivation is at. Well, part of it. Notice if you write r equals r, er, r, God, all right, let's just look at the math. If you take the derivative of the vector r with respect to theta, right, you can get e theta. That's just part of the definition of this this mess. You take the derivative of e theta with respect to theta, and you get negative er. You can do some substitution here. Like der dt is the same as der d theta times d theta dt, right? And this is how you can separate the variables and realize, okay, this component here is e theta, and this is d theta dt. So that's how you expand those formulas on the previous page. So let's look at the particle vector. This is basically, again, very detailed on how you do this. The velocity is just d dt r er. You take, again, you split the variables. It just occurred to me, I forgot what the hell this is called when you, it's a product rule, I guess. In math. Yeah, don't tell Krupa, I forgot. So, you know, this is how you get this this function here, right? This dr dt is d theta dt e theta, right? That's where that comes from. So that's the velocity vector, and then the acceleration vector is just taking the second derivative. Again, you can kind of go through this. I'm not going to be expecting, well, yeah, the derivation is kind of, you should be dealing with the final equations pretty much. But you should recognize in polar coordinates where these are coming from. Yeah, you'll also hear this referred to as polar coordinates. Yeah, cylindrical coordinates. So you can also use, you can take this, if you have something going on in 2 dimensions. So say, for example, the fire truck ladder, right? It can be extending, it can be rising and falling with theta, but it can also be swiveling, right? Those are what's known as cylindrical coordinates. So you'll typically have another position here, zk. So what we'll do is you'll have the theta as part of the xy plane, right? And then you'll have the radius will extend outwards, and you'll have z up and down. So you won't define this theta anymore. You'll define the theta that swivels around. And let's see, this goes through the derivation for position vector. Again, r, er plus zk. And remember, er is a function of multiple things, right? You've got theta and, well, here it is here, right? dr dt. You've got to separate to the product rule. And you get your acceleration vector by taking the second, or the derivative of velocity with respect to time. So again, it can be kind of complicated. Most classes, you'll probably take some kind of transport class in your junior year. Again, maybe senior year, depending on how your courses are set up. You'll probably do a lot of things like fluid mechanics. Fluid mechanics is one of those things where you do a lot of stuff in rectangular coordinates, and then they show you the derivations, and then you're just expected to be able to look up the analogous equations in the back of the book to figure out what set of equations you should be using. Let's see if I have. No, I don't have it accessible. I had a textbook with all the different coordinates in the back. This might have it. Let's see. And so typically you're introduced to it, and then in the appendix you'll have some kind of a set of equations that really help you figure it out. Let's see. This is a graduate textbook, so I don't know if it's going to have. Yeah, I'll look for it later. And there's another textbook that I have that's undergraduate textbook that shows that stuff. All right. So how does this work? Let's look at the rotation of this arm, right? You got this arm, and I don't actually know what's going on here, but you've got this arm that rotates theta with respect to time is 0.15 t squared, right? So as time increases, theta increases, and theta is in radians, t is in seconds. Now you have this collar here, B, and it slides along the arm, right? Such that the radius also changes with respect to time, right? So as time increases, it looks like this is decreasing, which kind of makes sense, right? This thing's going up, the arm's swiveling up, and this is sliding down. After the arm is rotated through 30 degrees, right, determine A, the total velocity of the collar, right? So the collar is moving, and the total acceleration of the collar, because the collar is still accelerating, and the relative acceleration of the collar with respect to the arm. So this problem combines a whole bunch of stuff in the polar coordinates that we've covered in rectangular coordinates. So the first thing we do is we can see, well, we're given the theta, right? So what's the time, right? So we're gonna find the time first just from this equation. And then once we have that, we can figure out, okay, what are the radial and the angular positions and the first and second derivatives, right, at the time, because you have the first and second derivatives for position are velocity and acceleration. And then you can calculate velocity and acceleration based on those equations. Then once you have all that information, we can go back to our concept of relative position or relative velocity. Now we're looking at relative acceleration. And we can evaluate that for the collar with respect to the arm. Oh, what happened here? Oh yeah, I think I left this. All right. Yeah, I put this in. All right, so in this coordinate system, this is just to remind you what's going on, right? Your velocity is the first derivative of r, or position with time, and then r d theta dt, right? And then your acceleration has all these derivative and terms for r and theta. So let's look at this. So the first thing is relatively straightforward. Remember, you work in radians, 30 degrees, because it told you it's in radians. So convert 30 degrees to radians, and then just solve for t, right? Straightforward. I think the only thing that people will screw up is forget to convert theta to radians here. So again, read carefully what the problem's asking. Let's look at the position vectors. So you've got r. Oh, what happened here? R is 0.9 minus 0.12 t squared. This was given, right? So you can figure out, okay, at time equals 1.869 seconds, right? What's that position? And that's that position there. The first derivative of that position vector is this, right? So you can figure out the velocity at that time. And then your second derivative, notice it's constant with respect to time. So this is experiencing a constant negative acceleration, right? So notice here with r, negative is indicating towards the origin, right? Towards the center of that radius of rotation. So just be aware, right? When you see a negative, if you want to get rid of that negative, you just draw in an arrow pointing to the, in the direction of the motion. And then theta. Theta starts off, right, is this. Your first derivative is this 0.30 t, and that gives you the radians per second. And then your second derivative gives you radians per second squared. Now, those are the individual components, right? We still need to plug them into the overall acceleration. What is, oh yeah, this is the relative. All right, let's go, let's start with this. This is velocity and acceleration of the, what are they calling this thing? The collar. Oh, I never remember the name collar. So let's look at the collar first, right? So the R, V sub R, right, is just, we've got this. It's the negative 0.449 meters per second. V theta, right? This component here, right? What's the velocity in the theta direction is R times the first derivative of theta. And we solved that already, right? We had 0.561 radians per second, right? So we have our theta component for velocity, 0.270 meters per second. So velocity is a vector, right? In some direction, and it's got an R component and it's got a theta component, right? So we can figure this out again, just using the Pythagorean theorem. We can figure out the magnitude of our velocity, and we can figure out the direction, right? So the velocity, and think about this thing, right? This is moving, this is sliding down the rod, and the rod is moving upwards. So this makes sense. Our velocity is sort of pointing backwards, and well, it's not pointing in the same direction as the rod. It's pointing horizontally in this case. I mean, not exactly horizontally. It's 31 degrees. This is at the instant of 30 degrees, right? Which again, kind of makes sense. Well, the velocity is it's got a component that's this way, and it's got a component towards the origin, right? It makes sense it would be slightly above that, that 30 degrees. Now we look at acceleration. Acceleration, again, these terms for acceleration, oh, I didn't write the equation here. The radial acceleration is a function of the second derivative with respect to time of r times r, the first derivative of theta with respect to time squared, right? Again, so we solved all that information, or all that stuff. We've got the second derivative, right here, which is the negative 0.24 meters per second squared. And over here, we plug in the r d theta dt squared, right? You solve for this, you wind up with the negative 0.391 meters per second squared. That is the acceleration, the r component of acceleration, right? So along the rod, right? Then you have the theta component of acceleration pointing this way. And you look at that, well, I mean, you don't actually know the direction yet, but it's going to be, it's going to be with respect to theta. So it's going to be this way or this way. Once you put the numbers in, though, you recognize, oh, you know what? It's negative 0.359 meters per second squared. So the acceleration, again, is in this direction. This is the theta acceleration. And then you put all the numbers together and you see, again, Pythagorean theorem, you get the angle. You see that your acceleration is 0.531 meters per second. Right, this is your magnitude, and the angle is in the 42.6 degrees off of the rod, like this, right? Again, it sort of makes sense. Your rod is accelerating up this way, right? This is experiencing acceleration towards the center, and acceleration in the negative theta direction. Oh, right. This is evaluating the acceleration with respect to the arm. So we're going to look at the motion of the collar with respect to the arm. So B, the acceleration of B with respect to, and we're calling this OA, right? That's the rod, OA. And this is just the second derivative, actually, of R. Now you can find, let's go back up here. You could find the equations and subtract them. Let's see, acceleration of B. Oh, Yeah, and I got to go through these slides and add it in. You basically just find the two components and you subtract them and you get your negative, well, you get your acceleration, the relative acceleration, right? So as far as this rod is concerned, right, with respect to the arm, the motion of the collar is accelerating negative 0.24 meters per second squared, right? And that makes sense, right? If you were standing on this rod, right, you're standing on this ladder and something's accelerating towards you, and this thing's moving, right? Well, as far as you're concerned, this thing's accelerating toward you, you know, just in this direction. You don't care about these other components. You're standing on this rod, and that thing's accelerating towards you at 2.40 meters per second squared along the negative radial direction. Yeah, so what's the summary here? Any type of rotational motion is where you should consider polar coordinates and see if they make sense. It makes it a fairly straightforward problem. Straightforward in the sense that you already have the equations, you just got to sort of drop things in to those components. I love this. One way to make the problem harder would be to ask you to find the radius of curvature in addition to the velocity and acceleration, right? So what's the radius of curvature? You'd have to find the normal components of the acceleration. And I'm not going to give you something like that. Your homework might have that. I have to look and see. I don't remember. This chapter covers so much stuff. Yeah, I'm not sure I even went into that great of a detail on the homework. All right. So this is group problem solving. Angular acceleration. So this is basically taking a similar problem to what we had, and we have different information now, right? Here we have the angular acceleration of this centrifugal arm varies by this equation. And they tell you the second derivative of theta is this 0.05 theta radians per second squared. And theta is measured in radians. If the centrifuge starts from rest, determine the acceleration magnitude after the gondola, they're calling it a gondola now, like it's a nice peaceful ride, has traveled 2 full rotations. All right, so what are we going to do for this? We're going to obviously define the coordinate system. We'll calculate the angular velocity after 2 revolutions. We can do that, right? And then we can calculate the radial and transverse accelerations. And then we'll figure out the overall magnitude of the acceleration. So let me work this out on the document camera here. All right. Any questions so far? This is blank. So we're given second derivative of theta with respect to time is 0.050 theta. Oh, I put a 0. Radians per second squared. And we're asked to find everything what's going on after 2 full rotations. So 2 rotations is, well, let's look at this. I'm going to draw this. I have to draw the diagram anyway. It's good to draw this out. You can see what's going on, right? My perfect circle. This is your 8-meter radius. Out here you have, I'm going to draw it over here just so I don't, well, yeah, I'll just draw it over a separate location. You're going to have a component like this, right? A component like this. This is your ER, and this is your E theta. And this right here is your, this gives you your acceleration vector, right? This stuff right here, these components. So 2 rotations, that's Remember, a full rotation is 2 pi, so we've got 2 times 2 pi, and this is going to be 4 pi radians. And now I'm going to write out the acceleration vector for this coordinate system. We've got r, second derivative of r with respect to time, minus r theta, so d theta dt squared. This is your ER component of acceleration, right? Then we're going to say it's plus r, and the second derivative of theta with respect to time, plus 2r dot, and I'm just going to say dots from now on, theta dot. This is your E theta vector, right? So these are the components of acceleration in the r and theta direction vectors. Let's see. One thing I want to do here is we're given theta double dot. So let's write this out here. This is d squared theta dt squared. This is basically equal to the first, or d dt of d theta dt. And then you can take this and you can expand this out to equal d theta, right, of d theta dt. This is going to give you d dt, right, d theta dt. So all this is telling me is, I mean, you probably could have seen it, but your theta, let's see, this is equal to theta double dot is equal to, let me just do this, d theta, or d theta, theta dot, theta dot. Right, that's all these are. This is saying it's the theta dot, or the second derivative of theta with respect to time is just the same as taking and multiplying d theta dt twice and taking the derivative with respect to theta, because we're given this with respect to theta. So we have to do some kind of I don't know, we call this mathematical trickery to get around this, or to get this, get this in some form we can use. So now you can rewrite this. Let's see. We're going to take the d theta, and we're going to get an integral. We're going to say theta dot dot d theta equals theta dot d theta dot. All I did was expand this. Let's see. From here, you're going to get the integral from 0 to 4 pi of 0.05 theta d theta. This is just plugging in your given information, right? Equal to 0 to theta dot d theta dot. If you take and solve this, you wind up with, you're going to have 0.05 theta squared over 2, evaluated from 0 to 4 pi, equals, we've got theta dot squared over 2, 0 to theta, oh, sorry, theta dot. Confusing myself with the dots. And if you evaluate this, you're going to wind up with, let's see, theta squared. Well, what is this? This is going to be 4 pi squared times 0.05 over 2. It looks like, oh, you know what? I canceled the 2's out. Yeah, that makes sense. So this is going to be, oh, it equals just theta dot squared. But this is going to be 0.05 4 pi squared. And that means theta dot is equal to the square root of this, right? Because this is basically theta squared. We know this theta squared. We're looking for theta dot squared. My dots are fading. 0.8 pi squared. And this gives us theta dot equal to 2.81 radians per second. So you get theta dot. That's probably the most involved part of this problem. Angular acceleration at 2 rotations. So now we've got theta dot. We also have theta double dot, right, up here, which we solved, right? So theta double dot, or which we can solve, is going to be 0.05. That was actually given to us, theta, right? Which is just 0.05 times 2 times 2 pi. Oh, that's the 4 pi radians. And that's 0.628 radians per second squared. So those are our thetas and our theta dots. Let me see here. Theta and theta dot. Yeah, that's pretty much it for the thetas. Now we got to look at our r's. So let me just write this as theta second derivative. Underline these. So we've got this one. We've got, well, this one and this one. They're both theta dot. We've got theta double dot. And then so we have them numerically, right? And then we're looking for r. We got to do r dot, and r dot dot. So r is equal to 8 meters. And the centrifuge arm is not changing with time, right? So that means r dot is equal to 0, and r double dot is equal to 0. Right? There's no change in r with respect to time. So your overall acceleration is just, what am I going to do here? I'm going to plug in. Okay, so I'm trying to keep this equation on the page here. I've got r double dot. So I'm going to have 0 minus r dot, or r is 8 meters, times theta dot squared. So I've got 2.81 radians per second squared. Let me put some units in here. This is meters. This is radians per second squared. And this is the ER component. Plus, I've got R again, which is 8 meters. Do this. Theta double dot, which is, oh, here, 0.628. And then I've got plus 2 r dot theta dot. Well, r dot is 0, right? And then theta dot, I'll just write theta dot in. It doesn't really matter what theta dot is. This whole term is 0. So I wind up with the acceleration is just negative 6. Oh wait, that's 63. 63.17 ER, right? That's the radial vector plus 5.02 E theta. And this is meters per second squared. Notice when you use radians, right? The radians kind of just go away. The radian is kind of just a dimensionless, it doesn't show up in your final answer. It's just meters per second squared. So this is your acceleration, and we want to find the magnitude, right? The magnitude is going to be these vector components, right? So we're going to have some now let me draw it over here. ER is going to be inwards, right? One, 7. And then E theta is going to be this way. 5.02. So your acceleration is going to be somewhat like this, right? Let me put M for magnitude. So acceleration magnitude is the square root of AR squared plus A theta squared. This gives you 63.4 meters per second squared. So this is the magnitude of the acceleration. And again, you could calculate the angle if you wanted to with respect to the tangent or the normal, just using your inverse tangent function. But that's the magnitude of acceleration. In fact, it doesn't ask for the direction, does it? Centrifuge starts from rest. Yeah, it doesn't really matter. I mean, it's the magnitude of the acceleration. So you know the components of the acceleration, and now you know the magnitude. And you do have a sense for the direction, right? It's just going to be, well, not fully towards the center, but sort of that way. Now, remember, when you're actually in one of these things, right, acceleration may be in that direction, but you're going to feel yourself sort of being pulled because you're in the gondola, right? You're being pulled, well, the acceleration is inward, but you're going to be forced to slide outwards, right? Because you're limited by the friction of the seat, and you're going to want to go sort of outward and back, right? This is how you're going to feel like you're being pushed, right? And that's your it's sort of a combination of centrifugal force and acceleration. So this is where I think the intuition fails us in these problems, is that, oh, I'm pointing to nowhere. This acceleration is, the actual acceleration is pointed like this. But if you're actually a person sitting in one of these things, you're going to feel like you're being pushed back this way, right? Out and into your seat, because the thing's accelerating around in a circle. Yeah, so that's the problem. All right, it's 9:53. Sorry about it, went a couple minutes over. Let me stop the recording.